Hello, thanks for joining us today. I'm Chris Ruoff, the publisher of Charged. Today's webinar is about selecting safe and reliable components for high voltage EVs, and it's brought to you by Knowles Precision Devices. After the presentation, there'll be a Q&A session. Please submit questions you have at any point during the presentation by clicking the Q&A button on your screen. The slides and a recorded video of the presentation will be available to view on demand after the presentation is complete, and we'll send out a follow-up email with links to download the slides and also view the video. So please welcome our webinar presenter, Steve Hopwood, Senior Applications Engineer and Engineering Manager at Knowles Precision Devices. Welcome, Steve.
Thank you. Let me share my screen. So thank you all. Thank you for joining us today. And as Chris said, today we're going to talk a little bit about high voltage components, particularly capacitors in the electric vehicle market. So just to introduce myself first of all, as you said, Steve Hopwood, I'm Senior Applications Engineer, Array Engineering Manager at Knowles Precision Devices. Knowles are a large manufacturer of specialist high voltage multi-layer ceramic capacitors, supply an awful lot to the electric vehicle industry, have been doing so for many years. My background is that I've been with this company for 25 years, been about 34 years in the MLCC industry in total. To give you some indication, some reference to that, when I started, people were just talking about this wonderful new idea of surface mounting components as opposed to putting them on wires. So I've seen an awful lot, been well used to this type of thing. So we're talking about high voltage in electric vehicles. So why are we talking about high voltage? Well, by increasing the voltage, we can do a number of things. Higher voltage means we can reduce the current, which means we lose the I squared R losses. It's a square of current, so the less current, the better it is. We can get faster charging by increasing the power. And we can do cost and weight reduction of the components in the vehicle. That particularly lines up to more range. So we're looking at faster charging cars with more range, more driving. And we've used the example there of 400 volts going up to 800 volts, which is very much the market trend that is happening at the moment. I just thought I'd throw this in, but I think we all know that electric vehicles, the range and the charging time are the critical factors to get right if we're going to improve the market. So this is a major study conducted in the UK, where I'm based, a couple of years ago, and it said that only around 25% of consumers would consider buying an EV as a main vehicle. This is despite the fact that they actually are going to be law in 2030 that you will only be able to buy an electric vehicle. So goes up to 50% if you can get a guaranteed range of at least 200 miles. But to get 90% of the population actually wanting the vehicle, you need to be looking at a range of 300 miles plus. And this just isn't going to happen with current technology. We need to get the voltages higher. And we are going higher. This is a scattering of headlines I just pulled off the web. It took me about 15 minutes to find them all. And they're all saying we're going to 800 volts. Got some big names there. We've got Hyundai, Delphi, Hitachi, Continental, Porsche. These companies are all saying that 400 volt is on its way out. We're going up to 800 volt. We're going higher voltage. We're going higher power. There is some discussion about going higher than 800, but at the moment, 800 is the target and 800 is where the market is going. So we know we're moving. This is happening now. Our customers are coming to us and they're telling us that the 400 volt battery circuits, the BMSs, the OBCs, and the knock-on circuits within the vehicle, 400 is dead. 800 volts is the future. 800 volts is where they're going. We get all these benefits from it. Therefore, this is all we're going to develop. But we need to think of the impact on the passive components. And as I say, particularly here looking at the ceramic capacitors, because it isn't as simple as just going up from 400 to 800 volts. The testing that's conducted on these circuits and the background information on this is critical. You cannot look at it just in isolation. So what is the impact that we're having? Well, the main concern, of course, with any electric system is that we have a risk of electric shock to the general public. It's not good sales practice to kill your main customers. And the mitigation, apart from lots of design features and safety features, is to do a high voltage test. And we're talking very high voltage. So we're not talking about testing at 500 volts or 1000 volts. We're going much higher. And this is having a knock-on onto the components that must be selected. And it's also where you are plugging in, you are having to consider safety rated parts. And this is mandated where connection is directly to the mains. So it must be covered under health and safety rules, individual country rules. But actually, the safety rated parts are they're looking to be very attractive because of their ratings with the other test voltages that are included. So these are the voltages we're actually seeing for testing. So the current system, 400 volts, we are routinely seeing our customers testing these circuits at 2000 volts AC, typically 50, 60 hertz, and 3000 volts DC. Upcoming systems, we're going to go up to 3000 volts AC, 4000 volts DC. And bear in mind that this is not a one-time operation. This is not going to do it in the factory and that's it. We're going to do it during the making of the board. We're going to do it during assembly of the product. We're going to do it when it's installed in the vehicle. We're going to potentially do it in service if the car goes in for a repair at any time. So we need to have components that will take this test voltage multiple times. And you've got to be very careful with this. Example I've thrown there, we've gone for a 400 volt battery system. We're looking to choose an AEC Q200 multi-layer. We need to be looking at something that's got at least a 2,500 volt DWV rating on it. 2,500 volt rated capacitor will have a 3,000 volt normally rated DWV, dielectric withstand voltage rating on it. Applied typically for 5 seconds. Important to note, in the vehicle, they're actually normally applied for 60 seconds. But there is the fact that you're doing repeat testing on this. We need to take that into account. If we just assume that we've got a 400 volt system and we can choose a 1000 volt part, we might test it. We might say it reaches 3000 volts, but we do that in our prototyping. No, it's not suitable for production use. You are overstressing that part every time it is tested, and that ultimately will reduce the reliability, result in lifetime problems. It's recognized that repeated DWV testing induces component weakness. There's a quote there taken from EN 60384-1. This is the main industry specification for capacitors, ICEN specification. And it states very clearly, repeated application of the voltage proof test may cause permanent damage to the capacitor and should be avoided as far as possible. So if you are looking at testing at 4000 volts DC, you need to be looking for a part that has a rated voltage of 4000 volts DC. It may sound as if you are vastly overrating the part, but you do not want to be risking the lifetime of your vehicle. The answer is engage with us, engage with your supplier. We know what margins we're allowing for in the design. If we don't think the part you're designing in will be suitable, we will tell you and we will suggest alternatives. Specify a part with a rating at least the required test voltage. So if you want a 4000 volt DWV, specify a 4000 volt rated capacitor. The slight exception is safety certified. That generally has appropriate test ratings, and I'll show you some of the ratings about the safety certified parts a little later on in the presentation. But this is where I like to frighten people, because this is what happens if you get it wrong. So these are a number of them. Most of those are actually real life circuit failures that have come back to us from customers. They've made a mischoice, bad choice in the component selection, and the result has been these failures. Parts have blown up, parts have gone short circuit. It's always important to remember that in a multi-layer ceramic, the component will generally fail short circuit. The market would dearly love to have a capacitor, that multi-layer ceramic, that failed open circuit, but it's not been developed. It is of interest, it is being looked at, but it is a number of years away. So this is generally is what you see if you get it wrong at the moment. So what's the impact going to be on the selection? By going for a higher voltage rating, you will be limiting the capacitance range. Very, very simplified equation. People who actually know multi-layers will pull the holes in it, but this is the basic fundamental equation for capacitance. A multi-layer, of course, puts multiples of these in parallel with each other to build up the capacitance. To give it a higher voltage rating, fundamentally, we increase the distance between the electrodes. We move them further apart. The critical bit to the voltage rating is the dielectric withstand in volts per micron dielectric material. Move it further apart, you reduce the voltage strain on the component. But in doing so, you reduce your capacitance. It's going to have some knock-on effects. If you need high capacitance, you may parallel parts up. If you do this, common pitfall, make sure your current paths match. I'm assuming here you're going to be doing this because you want ripple current to be going through. You're looking at it as a smoothing, filtering application. If you do the top path, where you go in, you put them all in a line and you come back out again, number one, the first component, takes virtually all the current. The resistance of the paths down to the end capacitor and back up again unbalance the whole circuit, and you get selective heating, you get selective short circuits, and you get component failure. Bad circuit design. The answer is what may be unusual circuit layouts. But if you look at the bottom one, the path in through the chip and out again is the same in each case. Yes, there will be some mismatch. There will be some unbalancing due to slightly different components, due to slight changes in the solder joints, due to ordinary handling and placing issues. But generally, they will be very closely matched. The top circuit I have seen used in application. I have seen major failures with it. Consider legislation for dual use. This may not be something you've come across at all, but it is something you need to be aware of. Dual use legislation comes from the Nuclear Suppliers Group, and essentially, to cut through all the legal speak that I put up there, what it says is that if a capacitor, and the one we're really interested in is number 2, if it has a voltage rating greater than 750 volts, a capacitance greater than 250 nanofarads, and a series inductance less than 10 nanohenries, you've made the fuse for an atomic bomb. That is, unsurprisingly, export restricted, and any component it goes into will subsequently be export restricted up to and including the vehicle. And this includes capacitors paralleled in an assembly or on a board if it is no other use than to provide capacitance. So if you were to take a lot of chips, put them on a board simply to increase the capacitance, and that board does nothing else, then it is treated from the eyes of the law as a capacitor. You're okay if all your tracks result in an inductance higher than 10 nanohenries, but if they don't, you are in problems. It is almost impossible to make a multi-layer ceramic capacitor with an inductance greater than 10 nanohenries. They're always less than that. So this is something to be aware of, to take into account, and if in doubt, consult. Verify that you're going to be okay on this. Safety rated capacitors I mentioned, very attractive because not only do they have very high voltage ratings and very high impulse voltage ratings, but they are tested externally to international standards. This gives a certain amount of certification, a certain amount of confidence in them. Their performance has to be good or they do not get the certificate issued. And it has to be independently verified. And this means they're actually increasingly being used in applications where you wouldn't initially say a safety certified was necessary. Obviously, they are necessary anywhere that the part is going to be coupled to the mains. So on your main charger systems, where you've got cables coming in from charger circuits, they're often mandatory. Elsewhere in the car, they just have some nice characteristics. And we see there, pleased to say we now offer the widest range of auto-grade safety rated multi-layers. But you can see we have 250 volt AC, 305 volt AC enhanced voltage ratings. We guarantee a 4mm creepage, but important, I think, for the automotive industry, we are the first company to have qualified them for DC operation. That's safety certified external qualification for DC, when we qualified to 1000 volts. We've also qualified them for high humidity robustness. So we've gone for the highest level there is. And of course, we've got the voltage ratings there. So we're talking about 4000 volts DC, 3000 volts AC, and we AQL them for 60 seconds of that. That's a sample test. And this means they're just ideally suited to 800 volt battery systems. The capacitance maybe isn't as high as you would like and as you would really wish, but it gives you a large amount of confidence in the component. And these we are already seeing a lot of interest in. We're seeing a lot of take up on. So this is something that is very keen on. I've just thrown in some typical example values there just for one of the ranges. There are actually a couple of other ranges, but if anybody is particularly interested in safety capacitors, I would urge them to contact us, obviously. You can see that they are UL and TUV certified. So this is an example of the safety certification that goes with these parts and the external test bodies that conduct the testing to verify them. So other things we've got to consider, normally multi-layers are not large components, but high voltage means you're going to get bigger. You've got to consider the creepage distance. We're going to be applying 4000 volts to this, and you need to consider the creepage and the clearances, otherwise you will get arcing occurring. So creepage, the distance across the surface of the multi-layer, and the distance between the pads on the board, so it's not just the component, will be a factor. Just this week, we've had discussions with a customer who was trying to use a component 5 millimeters long, Looks like it does everything he wants. He needs a creepage, minimum creepage of 18 millimeters to meet his standards. That's going to have an effect. It's going to have an effect on component selection. It's going to have an effect on board design. And ultimately, in there, it looks like he's probably going to have to just redesign his board to make sure the tracks, when they come out of a coated area, are at least 18 millimeters apart. So you're likely to be using a multi-layer that is larger than you've used before. The little example I'm showing there in the picture, I'm showing a 1206 and a 2220. There's a good reason for that, in that up until relatively recently, 1206 was considered the maximum size most people wanted to mount on a board. Obviously there we're talking about low voltage systems. The 2220 is now proving to be a very common size. Certainly being mounted on the board successfully. And this is the smallest size you can really start getting into the 4 kV, 5 kV ratings. You can get some parts at case size 1812, which is the next size down. But if you start going much below those in case size, you start getting more and more creepage, clearance and flashover problems. So there is a general trend going on. We're going from low voltage 1206 to higher voltage 2220, 2225. This is where we are now. We are increasingly seeing larger case sizes requested as well. So we're already moving up to the 4040, 3640 sort of size. Whether it will go any bigger than that, not sure. That is quite a large chip. But certainly those sort of sizes are regularly being used now, getting more and more common. And someone who is perhaps not aware or not used to handling them is going to have to learn a few more techniques. You're going to have to consider board bending. You're going to have to consider pad size, reflow profiles. It's something that's going to be more of a consideration, but it's something we can always help with. And the advice, as ever, all the way through this is talk to your supplier. Engage with us and we can help. The reason we're going bigger, apart from voltage flashover, is to get the capacitance back up as much as we can within constraints of the law, and ripple current. So the larger case sizes, thicker components has an impact on the way the heat can dissipate. Heat is a direct relationship with the ripple current and the equivalent series resistance of the capacitors. And that those arrangement of physical requirements are driving us to larger and larger chip capacitors. Flashover, creepage distance. So we've got some slides there, which are very nice, taken at a very high-speed camera, showing how a flashover propagates. So you can see it starts on the surface, grows, then the inductance of the chip starts creating a magnetic field and blows the arc away from the surface. Happens in the blink of an eye. You calibrate the laws of physics. If you have a distance that the voltage can create a corona effect and start the arc happening, it will do so. All our ceramics are tested to a comparative tracking index greater than 600. That's all our, the actual dielectrics that the bodies are made out of, which can help with creepage rules. But ultimately, you cannot choose too small a product unless you look at coating it. And that brings us on to a little bit about board design and coating. So you can reduce your creepage requirement if you take additional measures to mitigate flashover. Chances are you're going to have to do something to mitigate flashover anyway if you're doing about these high voltages. Conformal coating is the most widely accepted. Make sure the coating covers all the surfaces, and that includes underneath. One of the bigger problems we see is that the board is coated, but there's no allowance for that coating to go under the chip, and there's no slot under the chip to engage cleaning. If you leave flux under it, you will have problems at high voltage. Leave solder balls into it and you've definitely got problems at high voltage. It's better if you can get it lifted up slightly off the board, and we don't need to be talking legs or standoffs. All we're talking about is take the varnish under it away. Just creates a little bit of a gap where you can get cleaning fluid in and you can get conformal coating under. Increasingly, we're seeing slotted boards like the design we're showing in the pictures there, where a groove is put right the way through. That obviously gives you ultimate cleaning and ultimate coating. So if you dip coat that, you will coat all the way around, full 360 degrees, under, over the lot. If you can't go all the way through the board, can you go part way through a board? Can you route a recessed slot? Any of these will help. We have application notes on our website which help giving some suggestions. Most other manufacturers will do the same. It's always worth having a look at them, always worth looking to see if they can help. Multi-layers can crack. Anyone who's used multi-layers in large numbers for a long time is aware of this. It's still considered to be probably the largest cause of in-service failure, and longer parts can be more susceptible to cracking as a result of board stresses. So we've got some examples there of what a mechanical crack looks like, and it's essentially that 45-degree crack that goes from the end of the solder joint to the end of the solder joint. So the part is mounted on a board. The board is subject to bending or stressing. Doesn't have to be just bending. And the crack propagates from the two ends of the fulcrum point. If it goes through an area of electrical overlap, you will get failure. May not happen immediately. It may wait until moisture penetrates into the crack and along it, but there is a higher chance of it happening. And if it does happen, you get massive amounts of electrical damage, you get the component blow up, and you get a short circuit. So there we have our stress points. We can see the crack initiation point highlighted. It goes up to the other end of the solder meniscus, these acting as the two stress magnifiers when the board is bent. Normally the board bending is depanelization or snapping into place, some form of mishandling. Not always. You can get this happening due to board vibration in service. We've seen that relatively recently. Somebody had put chip capacitors down and then mounted large, heavy electrolytic capacitors on the opposite side of them. During normal operation, the board was flexing up and down. It wasn't properly supported, and the ceramic caps cracked. You can also get it, so people don't realize, if you have a very rigid board and you have a shock wave that travels down that board. So again, you might have a thick aluminium back to the board acting as a heatsink, or you might have a ceramic board, and when it's snapped out of its panel or it's snapped into place, you can actually get a shock wave travel down the board. I've seen that take every chip off a board as the shock wave went along it. So it's not exclusively board bend, but board bend is the way that it's characterized, it's measured, and it's checked. There are some mitigations. There's always mitigations when we know of a problem. The first one is technique known as open mode or open. Very, very important to realize that this does not mean it's a guaranteed fail open. It's only a mitigation against a mechanical crack. If you have an electrical short due to an electrical event, an overpulse or a breakdown due to a manufacturing defect, the part is still short circuit. But what you do in essence is take the active area of the electrode back into the chip, you take it away from the end of those stress points, the initiators. And then you hope that if the crack forms, it doesn't form through the overlap area. If it doesn't go through the overlap area, you are unlikely to get an electrical failure. If it's very severe, you may get it going completely open circuit, not completely unknown for these to be completely removed from the board. So you get a crack at both ends and the chip falls off. It's not foolproof. Say electrical failure, manufacturing defect can still cause that part to go short circuit. The tandem capacitor. Build two capacitors in series within the same unit. The idea here is that each of those capacitors in series is rated to take the full operating voltage of the line. So the example I've shown there is a 200 volt rated part. In actual fact, it's dropping that voltage into 100 volt steps. But they are designed so that if either one of those goes short circuit, the other end can take the full 200 volts. Again, same problem as with open mode. It's not foolproof. You could, in theory, get a crack at both ends that went through the overlap areas and took out both capacitors. If you have, for example, an electrical pulse down the line, it can blow up one end and then blow up the other end. If both ends fail, you are still short circuit. It's playing the odds. It's mitigation. It's not foolproof. It's not like some technologies where the part will fail and recover back to open circuit. Whenever you're talking about failures in ceramics, always consider the worst possibility that it may go short circuit. We actually don't like the idea particularly of designing a part with the intention that it will be allowed to crack. Our feeling is that a part that cracks is not a good part. We, along with a lot of other companies now, offer a flexible termination. We actually invented the flexible termination idea 25 years ago, and we have a long experience with it. We feel we still lead the world in this. And using our FlexiCap, our trademark for flexible termination, we can demonstrate the capability to withstand a board bend of at least 5 millimeters in a 100 millimeter span. Technically, it's actually a 90 millimeter span, but 100 millimeters has more of a ring to it. The actual requirement for AEC Q200 multi-layer ceramic is that it will withstand a 2 millimeter bend in a 100 millimeter span for a type 2 X7R dielectric, 3 millimeters for a type 1. But the industry really prefers to see 5 millimeters, and we can guarantee 5 millimeters on our ranges. It's just a matter of how the FlexiCap is applied, but we know what we're doing with it and we know how to do it. Wanted to just try and put that in some context. That is a 5 millimeter bend across a 90 millimeter span. So that is the state of the art for an AEC Q200 part. And you can see how the stress is happening directly underneath the bend head. The component has to be mounted directly underneath, and the component is then pushed for a deflection of 5 millimeters. In actual fact, if you're seeing that sort of bend deflection in process, you're actually pretty much neglecting the process. It's not a good process if you're putting that much bend in. But we appreciate that that is the requirement. We can hold that, and we are working to improve it. So we are working towards that. That is actually around 20 millimeter bend. And yes, we do have components that are surviving that degree of maltreatment and bending. And we do have 40-40 size components that are achieving that degree of mistreatment and bending. It's all R&D, it's all work in progress. But we don't see a particular concern with larger case size products, putting them on your board. It is largely a learning process, how you handle these parts, and a confidence. When you use them, you realize that they can be done. So we're coming to the end. We'll just some summary. So battery voltage is increasing. That's a given. It's not going to stop. As the battery voltage increases, the test voltages are going to be much higher than you maybe realize. They're going to be thousands of volts, and this will impact what is available and what you can use. The capacitor voltage rating is important. You cannot just assume that a 1000 volt part that passes a 3000 volt test once is going to be suitable. You will have life test problems with it, lifetime. You are probably going to see some case size increase. It may be more than you previously used. It may be more than you'd like to use, but it is going to happen. You are almost certainly going to be using some parts that are bigger. And you may be concerned about cracking. Good control product developments. Talk to us. If you cannot get the capacitance you need, you can look at doing paralleling of parts. Again, we're here to help. We're here to talk about it with you. But watch out for dual use restrictions. It's not a widely understood law. It's not a widely known law, and it's very easy to fall foul of. You're okay if you're doing your paralleling on your own circuit board that is also having another function. Give consideration to creepage requirements. Look at the board designs. Look at what you can do to put slots or grooves or something. Use coating if you need to use coating. It's a valuable technique. And give serious consideration to using safety rated capacitors where possible. They're good technology. They're tested externally, and they meet the voltage requirements that we are seeing for these high voltage 800 volt battery systems. So they are certainly worthy of your attention. So with that, thank you for your time. And I can see we have some questions. So let me have a look at that. And we'll perhaps have a look at some questions.
Yes, great. Thanks for the presentation, Steve. At this point, like you said, we're going to move into the Q&A session. So for the attendees, if you click the Q&A button on your screen, you can submit any questions you have. Like I said in the beginning, we're going to be sending up a follow-up email that contains links to view this presentation on demand and also download the slides. So yeah, Steve, if you could begin by reading the question aloud and then answering it. Thanks.
Okay, sure. So we have first question I see up there is, can we explain what we mean by dielectric withstand voltage? I apologize for this. When you're in the industry for so long, you use the terms that you're used to, and you forget that they're not maybe not commonly known to everybody. So dielectric withstand voltage is the test voltage, also known as a voltage proof or a withstand test or a flash test. So it's where you test a component or a circuit at a voltage considerably in excess of the rating, and you're doing it to weed out early stage failures. So for instance, in production, a 1000 volt rated capacitor may typically go through 100% test at 1250 volts. The safety capacitors I've been talking about, even though they're only 250 volts AC rated, 1000 volts DC rated, we 100% test those at 4000 volts. And the idea is to take out any, let's say, rogue failures, any rogue components. And that is referred to as the dielectric withstand voltage. With these bigger parts, is there a risk in production with cracking when placing these? I think we covered that on the presentation. Yes, there is. It's probably less than you realize. If you talk to us about it and if you consider it, then it's not something that's insurmountable. Question about the impact of thermal cycling, greater than 1,000 cycles. It's something, if you want to consider it in your application, then you will need to review it in terms of your specific board and component design. Part of the AEC Q200 requirement for component specification approval is that we do 1,000 cycles, and all the components within our range have to withstand that and pass it at the end with a maximum capacitance change allowed, and they have to be electrically good. So it is something that is tested automatically as part of the product qualification. However, it is done on a standardized test board, and we would always recommend that if you are doing it in application, if you're going to see that number of thermal cycles, then you should look at testing it. I would emphasize that to pass that thermal cycling, you will need to have a flexible termination. So FlexiCap if you are using a type 2 dielectric. Type 2 dielectrics are the less stable ones, the X7Rs, the X8Rs. Class 1 dielectrics such as COG, the very high stability, ultra high stability parts, generally don't need it. But if you have an X7R, then you will need it, or you will get cracking of the component and potentially the solder joint under high number thermal cycles. See what else. So someone said, when we say test voltage, are we referring to any end-of-line testing or general validation testing? Depends on the voltage we're talking about. So I think, as I just said, a certain amount of the dielectric withstand voltage is end-of-line testing, but we also will have general validation testing as well. So it's not practical, for instance, that you test 100% at 60 seconds. So that would be a validation test done on a batch basis. Depends on the test, depends on the product. Generally, I was referring to end-of-line testing, but not in every case. If you want a bit more clearer, feel free to contact me and we can sort of pick up on your specific requirements. Are there any stack-mounted MLCCs which are safety rated? Not that I'm aware of now. The problem you would have would be getting the very high capacitance and going through the things like the impulse test. Potentially in the future, but I'm not aware of anybody who is rating them now, not in terms of stacks. There are some people who are doing it for using low cap chips to get them through. Someone says you mentioned test voltage 4,000 volts DC for 800 volt DC battery systems. What are you seeing as a working voltage isolation levels? I'm not quite sure on the question there. We are seeing that the requirement for board test is around 4,000 volts DC. And that is every time the board needs its test to be done. I'm not quite sure what you would refer to as working voltage isolation levels. I think my interpretation would be that it's always going to be tested at 4,000 volts DC, and then it will be working at 800 volts DC with a ripple on top. When should I use an AC Voltage Dwv versus DC test? And I would answer that quite simply, when your specification tells you. We use a DC test as standard, but if the component has an AC rating, then we would consider it necessary to do an AC test, at least on a sample basis as well. But ultimately, it comes down to specification. What is your final requirement? Someone asked what voltage caused the flashover in the test image. To be honest with you, I can't remember. It's a long time since we did it. It was a part that was chosen, and then we pushed the test voltage beyond its standard testing. So it's not really relevant. It was just done to create a flashover. From memory, it was something like 3000 volts on a 1206 size component, but it is going back a long time on that. Okay, root cause for crack formation. Does material selection or processing or form factor dominate? What dominates? I'm not sure what dominates. Material selection and form factor do have an impact. So certain dielectrics, as I said in the presentation, are more prone to fail. Type 2 dielectrics are more prone to fail than type 1 dielectrics. They're just a harder product. Longer, thinner components are maybe more prone to fail, but it really comes down to how much stress you're putting them on. So a longer one, you will tend to be putting more stress on if you have board bending. My response generally would be, if you are having cracks, consider your processing. Try and eliminate it. We're getting to the point now where we can demonstrate quite significant board bending without any cracking. So while it still happens, and maybe it isn't always board bending, then we certainly need to take processing into account as well. How to choose safety caps between multi-layer or film? Depends on your application, it depends on your requirements. Both have their advantages, both have their disadvantages. Multi-layer ceramic will always be a much lower inductance than film. Film is considerably higher inductance levels. If you are working on a circuit that is doing smoothing or filtering, that can be quite important. You want to get the inductance as low as possible. On the other hand, with film, because you can just wind it larger and larger and larger, you can get much higher capacitance values by going for a much larger component. So it's horses and courses. Look at your application, look at what you need. I would say in the sizes where multi-layer is available alongside film, generally surface mount is now going to multi-layer. There's still a bit of through-hole film in that those small sizes, but increasingly film is being isolated into its larger sizes, whilst ceramic takes the small case size, lower capacitance values on the board. And finally, any feedback on capability of larger parts used in high frequency ripple currents? Yes, talk to us. It's not something we can answer just like that. You need to look at the component that's being used, the voltage, the capacitance value, and specifically start looking at the equivalent series resistance. The driving factor for the restriction on ripple current is the self-heating. So we look at the equivalent series resistance. We look at the case size and what power we believe that can dissipate. And that is directly related to the case size. So it's not an easy answer. And it's something that you really need to talk to your supplier on. We fielding questions on this several times a week. And we also have a test facility built up where for certain parts within certain limits, we can actually do this test and we can apply varying ripple currents and look specifically at the temperature rise that's occurring. So it's something that is a very common question, specifically something we look at, but you really need to talk with us or with whoever your supplier is on each individual specific application and your operating and test conditions. Actually, I just have another one come in. Field testing for isolation, we couldn't use in 500 volt. Will 1000 volt be enough to check loss of isolation testing on the 800 volt systems? I think the answer I've got to give there is go back to the specifications and see what you need to meet. So our specifications as component suppliers are being given to us by the our customers, by you guys who are working out what you need to do. And I would say 1000 volts check for loss of isolation on an 800 volt system is very much lower than I'm normally seeing. That 4000 volts, 3000 volts is coming from specifications. It must be laid down by the car manufacturer and must be coming from automotive requirements. It's too common to just be somebody who's invented it. It's coming to us from many different sources. So I think I've got to say, check your specifications, check what your customer requirements are. But it sounds to me a little bit low to be doing 1000 volt for isolation test. Okay, and with that, I think that's all the questions in the list.
Great.
So
Thanks, Steve.
thank you.
Thanks for
I shall hand back. And thank you for listening.
Yes, thanks for the great presentation, and thanks for all the great questions. As I said before, we'll send out a follow-up email with a link to watch this video on demand. Thank you, everyone, for attending.